Okay, that's 12:02, so it might be time to make a start. If Angie would like to move on to the next slide. She can. Okay. So welcome today to the QAAFI Science Seminar Series. It's my pleasure to introduce Anqi Lee. Anqi joined CNAPS as a PhD student 4 years ago on a China Scholarship Council scholarship and is also supported by FABA, and she's one of the first FABA PhD students. During her time with us, some of the highlights were winning a QAAFI 3MT People's Choice Award for the work that she'll be presenting today, and a QAAFI Travel Award, which she used to travel to Chile for an international symposium on the delivering functionality in food systems. She submitted her PhD just a few weeks ago. If you could go to the next slide, which will be me. I'm Bernadine Flanagan. I'm a research fellow in the Centre for Nutrition and Food Science. I've been here since 2004, so a lot of you might have seen me. And I'm one of Anqi's co-supervisors, co-advisors. Slide, please. I'd like to acknowledge the traditional owners and their custodianship on the lands of which we meet. Pay my respects to the ancestors and descendants who continue cultural and spiritual connections to country and recognize their valuable contributions to Australian and global society. Thanks. So just some housekeeping. Today's seminar is scheduled from 12 till 1, and we'll have a good amount of time for question and answers. So throughout the webinar, if you think of any questions, put them in the Q&A. Please don't use the chat function, just put them in the Q&A. And at the end, as the chair, I'll read out the questions for Anqi and she can respond, and hopefully we'll have some interesting discussion. The next slide. So Anqi. So it's been my privilege to be one of Anqi's co-advisors for the last 4 years. And in every PhD, there's always a few, troubles. That's what it's all about. Research is never a smooth road. But Anqi is remarkable for the way she meets every challenge with grace and perseverance. And her work here aims to advance the understanding of how food structures shape gut fermentability and how this will help develop health-orientated food systems. So welcome, Anqi, to talk to us today about some polysaccharide gels.
Thank you, Bernadine. Thank you for your introduction. Hi, everyone. My name is Anqi, and as Bernadine said, I'm the PhD. I'm still a PhD student right now, but I already submitted my thesis, waiting for the examiner feedback. And today I'm going to share part of my PhD project, titled "The Relationship Between the Properties of Food Polysaccharide Gels and Their Nutritional Functionality in Vitro." And here I too also acknowledge the traditional owners and their custodianship of the lands. And I also pay respect to their ancestors and their descendants who continue cultural and spiritual connections to country. I recognize their valuable contributions to Australia and the global society. As we know, the dietary fiber is recognized as an essential component of a healthy diet, and most of our daily intake of non-starch polysaccharides, often refers as to dietary fibers, come from the plant cell walls, especially the fruits, vegetables, and the whole grains. And the image on the right hand shows a simplified view of plant cells and their cell wall structure. The plant cell wall is rich in complex polysaccharides such as cellulose, hemicellulose, and pectin. And not just the plant cell wall, we can get the dietary fiber, the non-starch polysaccharide, including pectin, gum, arabic, alanine, glucomannan, cellulose. But we can also get the dietary fiber from the seaweed, bacteria, and fungi. For example, the cutland, gellan gum, sexin, bacterial cellulose from the bacteria, and agar, alginate, carrageenan from the seaweeds, and also the glucan, mannan, chitin, and chitosan from the fungi. But some fibers are refined as polysaccharide used as the processed food ingredients, but they may have the potential different to for the different potential to affect gut fermentation outcomes in diverse ways. Because they have a diverse origin, give them different structure and functions. So maybe both in the food application and inside the food body. And here's some dietary fiber application in food. As we know, because they have diverse structure, they can be used as the emulsifier, the thickeners, and also the gelling agents, which is the really important one of the important functionality in food applications. So they can be set by ions, just like the alginate and pectin can be set gels with the calcium addition. They can be set by the temperature modification. When we decrease the temperature, the agar can form the jelly-like dessert. And not just the cooling, we can form the gels by heating. Like the methicellulose and kaolin, when we heat it, they can form the 3D gels. And they can be used as the fillings and the meat analogs as well. And also, the chemical and enzyme-mediated gels can be formed. For example, the conjugate glucomannan can form the gels with the heat and the alkali condition. And sugar beet pectin can form gels with the lactase addition. So as we've seen, the gelling polysaccharides are widely used to create texture in food. But in food design, we often focus only on the texture and overlook the nutritional side. So two polysaccharides may have the same texture but behave really differently in the gut. So we have less focus on its nutritional outcomes. And when dietary fiber is added to boost the nutrition, it's usually just think about the amount, but not the form. So that's why it is really important to look beyond texture and amount to consider structure and function in digestive system. So understanding how these different polysaccharides behave during digestion is really important. So now let's take a quick look at the journey of the dietary fibers take through the human digestive system. When we have the dietary fibers consumed in different forms, both in plant cell walls and the gel particles, when they go to the mouth, they can be reduced to smaller particle size. And then they go to the stomach and small intestine. But different from the other nutrients in the food, the non-starch dietary fibers and polysaccharide, they escape the digestion due to the lack of the enzymes we can get from our cells. So most of them just reach the large intestine as their original form. For the easily fermented and polyfermented polysaccharides, they can contribute to the short-chain fatty acid production, which is the beneficial metabolites, and also can help the stool bulking. When the dietary fiber in the large intestine, as I mentioned before, the easily fermented polysaccharides, they can be used by the gut microbes to produce the beneficial end products, short-chain fatty acid, mainly include acetate, propionate, and butyrate. And butyrate is also considered as the key to prevent the bone cancer. And also they can contribute to the microbiota modulation in our gut. But But as a key parameter of the fermentation, the kinetics is one thing we need to consider as well. For the faster fermentation, it may result in excessive gas production that may give you the discomfort. But the excessive gas production, instead of that, the steady and consistent fermentation can contribute to high butyrate production and wider short-chain fatty acid distribution throughout the column, especially in the distal column, where the bone cancer always happens. And don't forget the poor fermented one. They can help the store forming because of the hydration property to help us modulate the gut transit time. So to conclude what we have known, we already know the non-starch polysaccharides are widely present in everyday food. For example, they can be used as the gelling polysaccharides as the texture modifier. And non-starch polysaccharides plays a key role in the large intestine. But we have no idea, do different gelling polysaccharides have different fermentation outcomes, and what physicochemical factors affect the fermentation kinetics and metabolite production? How about the particle size, the concentration, and the solution and gel form? In order to answer this question, here's my project scope. In the first and the second study, I investigate the particle size and density effect on algae and pectin gel particles. These two share the similar gelling mechanism, which can be stabilized by the calcium addition. And the first study more focused on the millimeter size range, and the second one into the smaller size range. And in the third study, in order to know the fermentability of different gelling polysaccharides, we did in vitro fermentation test for the commonly used gelling polysaccharides we can use in the food applications. And for the fourth one, I investigated the University of Physicochemical effects on the in vitro fermentation dynamics, but with the different gelling polysaccharides we get from the third study. So the first one, let me introduce the impact of pectin and alginate gel particle size and concentration on in vitro fermentation. And this one has been published on food hydrocolloids. So if you are interested in it, you can have a look on this one. In the first study, I used the algae and pectin gels by using the different method to give the wider size distribution. By using the dripping method, I got the algae and pectin gel particles ranging from 2 to 4 millimeter diameter. So this one, by adjust the needle size, I got 2 different sizes. And in order to get the smaller one, I used the emulsion-based method. Because of the high viscosity of alginate, I cannot use the dripping method to produce the smaller one. So also in this one, I also have the solution as the control. So here I have the alginate pectin, and with 2 to 4 from 2% and 4% concentration, and the 3 different sizes. An alginate pectin solution as the control. And we got the human fecal inoculum from 6 healthy humans without any antibiotic intake in 3 months, and used this gas recording system to monitor the gas production and also detected the short-chain fatty acid during the 48 hours of fermentation and also the remaining substrate. Here's the gas production curves of the pectin solution and gel particles. As we can see, the gel production reduced by the gel formation because the pectin solution fermented faster than the pectin gels, no matter the particle size. And also the similar phenomenon can be seen in the alginate system. In here, even the alginate solution fermented lesser than the pectin solution is still much higher than all alginate particles. So here we can know not the kinetics, but also extent the fermentation of the pectin is larger than the alginate. And also the solution has the faster kinetics and higher extent than all the gel particles. And not just the gas, this phenomenon can be seen in the short-chain fatty acid production as well. The alginate solution produced more total short-chain fatty acid than the alginate gel particles. But within the alginate gel particles, even the particle size and the densities are different. Not significant differences can be seen within them. So the particle fermentation was not affected by particle size and concentration for the ranges we studied of the alginate. By comparing the alginate with the pectin showed a faster fermentation rate and a higher short-chain fatty acid production than the alginate. But interesting is we can see the small pectin gel particles and pectin solution cannot see significant differences. This shown the small pectin gel particles suggest a solution-like behavior in the short-chain fatty acid production. To conclude the first study, we know the fermentation of the gel particles in the size range from 2 to 4 mm is lower than the corresponding solution, but shows little variation in concentration or particle size for either polysaccharide. The gel particles about 0.5 mm size of pectin show the similar fermentation to the pectin solution, but this similar phenomenon cannot be seen in the alginate system. And compare the pectin to alginate, the pectin gels and solution are fermented faster than the corresponding alginate system. So based on the second interesting finding from this first study, I designed the second one. So in the second one, I focus on the smaller size range of alginate and pectin gel particles in order to eliminate the concentration and the component differences. I just alter the stirring conditions and gelling conditions to make sure they have the similar component, but just the size difference. So here from the master size distribution, we can know I already got the alginate and pectin gel particles ranging from 100 to 300 micron. And here's the gas production of the alginate and pectin systems. We can also obviously see the pectin system fermented faster than the alginate. And this similar phenomenon can be seen in the total short-chain fatty acid production as well. In order to know their substrate degradation of the alginate and pectin gel particles, I used the confocal to observe their the alginate and pectin gel particles. So here, the green background is the stained skim milk by the fast screen, and the black hollow here represents the gel particles. So here, from the fresh one, we can see the pectin gel particles as shown in the black spherical shape with strong contrast to the background. But when it comes to 6 hours, the contrast is weaker, which means the structure of the pectin gel particle is not strong enough to let the background milk get into the gel particles. And after 24 hours fermentation, there's no pectin gel particles can be seen in the view. But different from the pectin ones, the alginate gel particles can be always seen throughout the 48 hours fermentation. Even after 48 hours, we can still see the alginate gel particles in the view. And also we can see the substrate dependence differences in the microbial community composition. Here, I did the sequencing to see the microbial community of the alginate and pectin systems at 24 hours for all the alginate pectin gel particles and solution. And here we can see the alginate substrate, they clustered at the left corner and the pectin at the right corner. So this indicates the substantial substrate dependence differences in the microbial community composition. In order to have a clear understanding of the physical form on the microbial community composition, I just exclude the inoculant to just show the alginate and pectins in this figure. And along the PCOA, solution samples diverge from the gel samples. Here's the alginate ones, and indicating their physical form, but not for the particle size. The range we started also contribute the microbial variations. And on the right hand, we can also see the pectin system. So this suggests that the substrate accessibility and the structural constraints can influence the microbial fermentation dynamics, but the particle size has had minimal impact of the microbiota composition, as gel particles of different sizes form the tight grouping within each substrate type. So to conclude the second study, we found the pectin was fermented more rapid and extensively than the alginate across both solution and gel form. That's the same from the first study. And also the gelation slowed the fermentation and reduced the short-chain fatty acid production. Reducing the particle size partially alleviated the matrix constraints in pectin system, but had limited effect in the alginate systems. And microbial community composition was influenced preliminary by the polysaccharide type, like the alginate pectin over here, but the physical form can acting as a second factor. In order to know their fermentability of the commonly gelling polysaccharides. In the third study, I tested the fermentability of the conjugate glucomannan, mesocellulose, sugar-bit pectin, coltan, agar, agarose, and gellins in this study. And here's the gas production of the all gelling polysaccharide powders. Since the fast gas production and the high gas production volume, we can know the conjugate glucomannan, the coltan, and sugar-bit pectin can be characterized into the readily fermentable polysaccharides. But in contrast, the one gathered in the bottom can be characterized as the poorly fermented ones. But can the gelation condition change the fermentability of the polygellin, agar, agarose, and mesocellulose? In order to answer this question, I designed the powder and gel cubes fermentability test for the agar, agarose, and high acid gellin for the to answer this question, and also the coltan as the positive control included in this one as well. So here's the gas production of these polyfermented gel powders and the curdlan as well. And we can see the gas production for the polyfermented ones are really low compared to the curdlan, no matter it is in the powder or in gel form. And we can see on the right hand is the total short-chain fatty acid production and the butyrate production of all this. And it's interesting to see even the gelation decreased the total short-chain fatty acid of the curdlan. The butyrate production is higher than the curdlan powders. So the gel formation reduced the extent and rate of fermentation of curdlan, but it gave curdlan a steady and a consistent fermentation, contributing to the higher butyrate production. And gel formation did not promote the fermentation of the polyfermented ones. So we may ask why the curdlan can ferment it faster, even if it's not commonly used in the food additives, because the curdlan is always its structure has similarity from the glucose, the glucan we can get from the fungi and the cereal. So that the gut fermentability we think depends the familiarity of gut microbiota to the classic linkage type rather than the polysaccharide itself. So based on the highly fermented one, curdlan, KGM, and sugar beet pectin, I designed the last study, the gelation, particle size, and concentration influences on the in vitro fermentation of curdlan, konjac, glucomannan, and sugar beet pectin. In this one, this time I produced the bulk gels with different concentration. And by cutting them into the 5mm cube and using the homogenizer to blend them into the 100 micron size. And also the solution and suspension as the control. So put all of this into the in vitro fermentation to test their fermentability dynamics. Here's the different physical properties of the gel cubes and particles. In order to get the gel particles in the same size, we just cut them, and to detect their mechanical response, I used the compression test. And here's the apparent compressive modulus of the curdlan, KGM, and pectin gel cubes. And here we can see the differences in the concentration effect and also the different gelling mechanisms. We can see the pectin ones show the lowest. This may contribute to their, this may because of the point coadditive links, cross-link of the sugar beet pectin. But when the KGM formed the largest one, because the chain later association formed during the heat and alkali treatment. The curdlan formed gels by the conjunction zoom cross links, so give the strengths between the KGM and sugar beet pectin. This similar phenomenon can be seen in the gel particles as well. So by using the gap-dependent rheology, we detect the mechanical response of the gel particles. By compressing the 50% of the maximum gel particle size, I got the G prime of the gel particles. And the similar phenomenon can be seen as well. The sugar beet pectin show the lowest mechanical response, and KGM showed the largest one. And this relatively low modulus of the sugar beet pectin can be explained by these point coercive crosslinks. And here's the short-chain fatty acid production of the Kirtland, KGM, and sugar beet pectin. So we can see the Kirtland, KGM, and sugar beet pectin exhibited the total different short-chain fatty acid profiles. Even we use the the gel formation to decrease the short-chain fatty acid throughout these three. We can also see the sugar beet pectin exhibited the highest total short-chain fatty acid compared to all the Kirtland KGM systems. And the physical form gives the most consistent and steady short-chain fatty acid production throughout the 48-hour fermentation. So we can see, especially for the Kirtland, it showed the highest butyrate production in the Kirtland gel cubes compared to the Kirtland suspension and the small Kirtland cubes, gel particles. And here's the microscopy observation of the Kirtland gel particles and KGM and sugar beet pectin. So here I used the calcifluoride to stain the Kirtland and KGM. And the pectin gel particles were stained by, cannot be stained, so use the negative staining to stain the background. And here we can see the different morphology of the Kirtland and KGM and pectin gel particles. So instead of the spherical formology, the KGM shows the sheet-like structure. It's more like the fragments of the whole network. And by comparing their formology change throughout the fermentation, we can see the sugar beet pectin shows the faster degradation compared to the Kirtland and the KGM system. And using the Cyto 9 stain, I used the mixed stain to stain the gel particles and also the microbes. And we can see the microbes just mostly located on the gel surface. So from this study, we know that both chemical structure and physicochemical properties influence the polysaccharide fermentation behavior. And the gelation generally reduces the fermentation kinetics by restricting the microbial accessibility. Also, the extent depends on gel network structure. And stronger and denser gel structure, particularly the KGM gels, impose the greater fermentation constraint than the point cross-linked sugar beet pectin gels. Particle size and concentration modulated the fermentation kinetics through changes in surface area and matrix density. And microbial utilization in gel system appear to occur mainly at the particle surface and contact regions. So from this study, we know the factors can turn in the in vitro fermentation of gelling polysaccharides. So the chemical structure is the primary factor, which at the molecular scale. And by give the structure, we can constrain the microbial accessibility to decrease the fermentation. And also the density, concentration, and particle size can help adjust the fermentation kinetics, but has minimal effect. So from this one, we already know the readily fermentable polysaccharides can be used by the gut microbe to help the short-chain fatty acid production. And fermentable polysaccharides help more in the store hydration. And the medium fermentable polysaccharides can give the steady and consistent fermentation, which can contribute to sustained short-chain fatty acid production. So we already know not all the dietary fibers behave similarly in the gut. Also, they can be labeled as the food additives, the food dietary fiber as well. The polysaccharide's chemical structure remains the primary determination of the fermentability and microbial utilization. And not just the chemical structure, the physical structuring can provide a strategy to modulate the fermentation kinetics and metabolite production. Combining the polysaccharide selection with structural design, for example, the structuring particle size and matrix density may enable targeted modulation of gut fermentation behavior. So in this study, the pectin and KGM solution, for example, can be seen as the readily fermentation polysaccharides. And given the structure, the pectin and KGM gels can be seen as the medium fermentable ones. As for the alginate gels, agar and gelen, they can be characterized as the polyfermented polysaccharides, helped more in the store hydration and store forming. So last but not least, I would like to say thank you to all to my advisory team and also the prefab team. And the research fellows and the HDR students help in the in vitro fermentation experiments. And also, I would like to say thank you to the Australian Food and Beverage Accelerative for their financial support. So I will hand it to Bernadine to facilitate the Q&A session.
Thanks very much, Anqi, for thoroughly describing your PhD thesis for us. I'd like to invite anyone, if they have any questions, to put them into the Q&A, and then we can start with them. But obviously, this is something I really like as one of your co-advisors, but you've got some data that is really interesting. So for study 2, it's really fascinating how you've got the two differences between the big difference between the alginate communities and the pectin communities. Do you have any idea of which bacteria are changing particularly in them? Is it like an overall community change, or is it individual groups that are changing, like small levels?
Well, that's analysis is being conducted at the general level. So that's more about the at that level the differences, and yeah.
So do you see like is it most of the things are changing or just a couple of bands? So, with your relative abundance, is it the most abundant ones that are changing, or the lower level ones?
Thank you for this question. Maybe I can later I can show you the yeah, the top 50
This is
general.
very fresh data.
Yes, that's the relative abundance of the these gel particles and solutions. So we can only know their differences, but I cannot answer is that the and comes from the large ones or the small ones.
Okay, cool.
communication.
Yeah,
Communication.
it's just an amazing how much it splits because often there's the idea that, different bacteria could achieve the same thing, but in this one you've got obviously recruiting different bacteria for different roles. Okay, so why is the molecular structure the most important factor for deciding the fermentability? Why do you think that is?
I think that's comes from um, the gut microbe, whether they can degrade um, the um, the polysaccharides we intake. So because for example, the agar and agarose, they have the structure that gut microbe are not familiar, so they don't have the enzyme to break down that structure. I think that's the key that's the key determinant for that. So if they cannot, if the gut microbes do not cannot have the enzyme to break down the linkage, the glycic linkage, um, any other um, uh, the physical chemical property change cannot have any effect on that results.
It's fascinating. And also um, the differences in the particle sizes. So uh, it did make a difference for some of them, but not for everything. So for Curdlan, the big gel, you see a difference between the big gels and the smaller pieces, but is that right?
Yes, yes. I think that may comes from the different gelling mechanism. As
Mm.
I and maybe I haven't explained it fully. So the by comparing the sugar beet pectin and the KGM, they are when they are in solution, they can be faster fermented. But when they into the gel particles, the KGM fermented much slower compared to the solution. But the sugar beet pectin gel particles, they fermented really similarly to the to its solution. Maybe that comes from the loose connection and the loose gel network of the sugar beet pectin. But for the KGM, it's like the more dense one, just like the cellulose, the fiber structure. So that physical constraint um, um, just constrained the microbial accessibility to the substrate and to the so make it difficult for the microbe to use the KGM. So I think that differences comes from the gelling mechanisms.
Mm. Thanks for that, Angie. Can I ask you which one you would like to eat of all of your polysaccharides that you've shown us today? Which would be the nicest one to eat?
Well, the nicest, well, that's a really interesting question. I think the only one we can eat and we can find in the local market is the konjac noodles, the konjac ones.
Okay.
Um, that so maybe that's my choice, but because the other gelling polysaccharides, they're mostly used as the food additives
Mm.
in the different food products. So my choice will be goes to the KGN, the konjac noodles.
Even though they're not very fermentable, or they're more fermentable than the agar. So,
Yes, yes, they are not that fermentable as the KGM solution, but they can have the steady and constant short-chain fatty acid production in my gut. So they can not just give me the short-chain fatty acid, they can also help me to form my stool. So maybe give me a wonderful experience in the toilet.
oh, well, it's important consideration. And what's your future work going to be on this project?
Well, so as I include in my presentation, the last study, I just showed fermentation kinetics and metabolite production. So I would like to see more the microbial community response in this system. So I would like to do more study about this.
Okay. So I can't see any questions coming through in the chat, which could be a failing on my end of not being able to see them. But if anyone had any burning questions for Anqi, I'd like them to speak up now because she's waiting to go on holidays. So she's just submitted a thesis and she's been preparing for this talk. She kindly waited to do it for us before she jets off back home for a well-deserved break. So if no one has anything further, I'd just like to thank Anqi again for telling us all about her project and her future directions, and wish her all the best of luck for her all of the things she still has to do to get through her PhD. So all the very best. So Anqi, could you just move to the last slide, please? I'd like everyone to keep their eye out for our next QAAFI Science Seminar. Go to the QAAFI Seminars webpage. Also, if you have any interest in doing a QAAFI seminar, we'd love to hear from you. We always interested to hear what you have to say, and it's a great way to get your message out. All of the QAAFI seminars are loaded onto YouTube, so everyone can find it at a later date if they can't attend on the day. Thanks everyone so much for coming, and get in touch with Anqi if you have any more questions about her work. I'm sure she'd be happy to hear from you. Okay, thanks very much. Bye.
Thank you. Thank you, everyone.